All right, so I think we are ready to get started. And let me check a few things. Okay, the mic is good. All right, so I'm not sure how many of you did the exercise that I said, well, it'll be helpful that you guys do this. So even if you have just taken a look at it and not actually work on it, it will still be really useful. Or if you just kind of reviewed what we talked about, how we did it in class, and not actually do it, in this particular spreadsheet, that's fine too. Okay, but you still need something to kind of keep that information in your head. Okay, and that's going to be even more important over the weekend because we tend to forget all the things that we learned over the weekdays, over the weekend. So we're gonna start with this one. In other words, I'm gonna work this whole thing out. So this way, you guys get quote unquote the answer. Um, so I'm gonna get started here. I'm not gonna wait. Some people are gonna be a little bit late, but that is not unusual for this class. So if you want to, I can see one person is already in. So if you want to, you can go back to the spreadsheet and open your view. So this way you have control over, what you're seeing. So my insane scrolling is not going to bother you as much. All right, so we're going to get started here. So in this class, okay, we separate the propagation because of the node connectivity from the changes because of the behavior of the devices. So that's what we're going to do is to continue to separate those two. So the first thing we need to do is to look at how is the change of the input pin is going to affect the other ports because of node connectivity. In the other class, a few people claim that they are visual people, so it really helps to have a diagram, to help them. So in this class, I think one thing I could do is to reuse the diagram from the other class, but what I really wanted you guys to do is to come up with your own picture because we have been talking about this already. So it would actually be very beneficial if you have your own picture so you can actually see all that. But I'll try to be kind and kind of include the picture here for those of you who are more visual. Okay, why is it not copy and pasting into here? Okay, copy and paste. Nope, doesn't want it. Does not want to do that at all. Paste. Nope. All right, so I can't really paste it from the other spreadsheet. So we'll just go for the color. So the idea is, once we have everything color coded, it really doesn't matter whether we look at the picture or not, because all we need is a mechanism to find out what do we need to update, right? So color coding is fine. Looking at a diagram is fine too. If for those because this other spreadsheet is also available, let me just kind of put the link um, somewhere. Okay, let me do this. Okay, this is the link. I'm gonna put the link over here. So this way, if you want to open the other spreadsheet on your end, you can do so. I'm not gonna look at the picture, okay, because I want to kind of train everybody not to have to rely on the picture to get this done. All right, so enough said, enough words. So I need to look at all the green ones. So they're all going to get zeros. And I have to look at the blue ones. They're all going to get zeros too. So blue and blue. There we go. So that basically includes everything that are updated because of the two input pins all being zeros. So I'm going to boldface all of these and then put question marks. Maintain the question marks everywhere else. So we just have a whole bunch of question marks because we're trying to figure out, what is going to happen. So in here, I'm just going to say node connectivity like that. And now we have to look at the actual effect of the devices. In other words, after a certain propagational delay, after a very short amount of time, The devices that experience an input, a change to at least one of its inputs, is going to change the output. So this is where we'll try to figure out how the output of devices are going to be changed, if any, because of the input pins changing. That's the purpose of row 6. All right, so tell me which devices have at least one of the input pins getting changed. So we'll go through these one by one, okay? This way we won't miss anything. So do you think the gate N, which is a NOT gate, has one of its input pins changed? Just look at the bold face, yes, okay. So we're going to put a question mark or an underscore here, just a placeholder, so I can remember to go back and check that one. What about N1? Does any of the input of N1 change? And therefore, we need to figure out this output? Yes? Okay, all right. I just want to make sure everybody knows how to do this, okay? And then for N2, yeah, I think its output is we need to try to figure out the output because at least one of the inputs of N2 got changed. SR, not so, okay, because the S and R remain as question marks, so none of the inputs of the SR latch got changed. So now we got these 3 underscores to figure out. So let's figure out the output of the NOT gate first. What do you think it's going to be? It's going to be a 1. Very good. Oops. And this is also going to be an update because it used to be unknown and now it is 1. So it has to be has to be bold-faced. What about the output of N1? It's 1 again. Very good because it is the result of 0 NAND 0. And it's also a change from unknown and therefore it is also bold-faced. What about the output of N2? We only know one of the input of N2 being a 0. What would be the output of N2? Yes, it's also a 1. Very good. All right, excellent. So now we have figured out all the changes due to the nature of the devices after a propagational delay. And in this class, the convention that we use is we do not mix up the node connectivity with oops, I forgot. This is a question mark. So these are basically just copies from the previous row because they did not change. And let me just double check because sometimes I copy incorrectly. Yep, that's it. All right, so the next one is going to be node connectivity. In other words, we look at how the ports are connected by the nodes, and then we go like, okay, this one here going to spread to all the other orange, labeled, things. So this one is also going to go to this one because both of these are in orange. And then this particular one here is going to everything that is labeled, that is colored yellow. So there's one, and the other one is over here. And then we also got this one, which is purple. So this purple also updates the other purple one like that. And all of these need to be highlighted. They all need to be bold-faced because they are all changes from what they used to be before the the propagational delay. So all of these are highlighted, and then the rest we just copy. Okay, not a problem. Question mark, question mark, question mark, and question mark again. All right, so now that we are done with the node connectivity part, we are ready to wait a little bit for propagational delay. And then we also want to look at, okay, if at least one input is changed, we want to look at the output of those devices and see if anything is updated, right? So we look at the NOT gate N. The NOT gate N does not have one of its only input changed, so there's nothing to worry about this one. We look at N1, and you can see how both inputs of N1 have not changed since the node connectivity row, so we don't have to worry about that. And we look at N2. So N2, we kind of need to figure out what is output again because in1 of N2 just got changed. So we need to kind of leave a little underscore here so I can go ahead and figure that out later. And then the SR latch is also kind of in the same situation because both of its inputs got changed from unknown to 1 and 1. So we need to kind of think about how its output is going to be affected as a result. The Q and NQ are just pins, and pins we don't have to worry too much about the updates after propagational delay. All right, so now we go back and look at all the underscores, and then we try to figure out, okay, what is going to happen to the output of N2 now that we know one input is a 0 and the other input is a 1. The answer is the output is going to be it's going to be a 1 because 0 NAND 1 is 1. Okay, so we put a 1 here. And this one, we don't have the boldface because it was a 1 already. So the quote-unquote new update is not exactly changing it. So we don't have to boldface it because it's not going to trigger any additional changes. So we look at the output of the SR latch. Both inputs of the SR latch are now known as 1 and 1. So what is going to be the output Q and NQ when both inputs of the SR latch are 1 and 1? They're unknown. They're maintained. Okay. In other words, we're not quite sure what they are, but whatever they are is whatever they used to be. Okay. So once again, because this is not a change and this is also not a change, we do not use boldface at all. So that means now that we have figured out all the potential changes of outputs and none has changed, now we have arrived at a steady state, which means all right. So no further changes will occur at this point, unless we change one of the input pins. So once again, we have arrived at a steady state, and that's the end of step 1. Okay, so are we okay with all these steps at the end of step 1? We really do not know what Q and NQ are going to become. We do know some of the states inside the machine, but from the outside of the this is not an SR latch anymore. By the way, this is a level sensitive D flip-flop, but we really cannot tell what the output of the D flip-flop is going to be. It remains basically uninitialized. Are we good so far with the analysis? It is not so much that the zeros and ones are important. It is the process, how we go about doing this, that is important. Okay? All right, so when this is all done, I am going to kind of get rid of some of the unused rows. Okay, right click and say delete row 10 to 13. And now we continue with this. Okay, so what we do is we copy what we had before for all of the other zeros and ones and question marks, because this becomes the next initial state. And the change is also highlighted by the 1 here because we are changing the EN pin from a 0 to a 1. That's the only change for the entire circuit. So once again, the first thing we do is we use node connectivity to figure out what else is going to change to 1 because of the electrical connection between the ports. So this is in blue, so that means everything else that is in blue will also get the 1 automatically, like so. And then that's the end of it. Okay, we have to remember to boldface every single one of these because they are all changes from what they used to be, and then the rest we just copy. Okay, not a problem. So we'll copy the rest like so. And I have to be careful because sometimes when I copy incorrectly. So now that we have figured out all the changes because of node connectivity, now we can wait a little bit, okay? And then we determine what would be the output of the devices where at least one of its input has changed. So first of all, we have to identify the outputs that might have changed because of the changes. So we look at N, we go like, I don't think N is going to change because its input did not change. We look at N1, one of its input got changed, which is this one here. We probably want to kind of double check and make sure, well, not make sure, but we want to double check to see if the output is going to be changed. We look at N2, once again, one of its input got changed, so we should go ahead and figure out its output. We look at the SR latch, nothing, okay, because the 1 and 1 are maintained, so we don't have to worry about that. So we only got 2 output pins that we need to kind of figure out at this point of time. So from the perspective of N1, both one input is a 0, the other input is a 1. 0 NAND 1 is a 1. So it is maintaining its output as a 1, even though one of its input pins has changed. It doesn't change the output, and because there's no change of the output, it is not going to be in bold phase. We look at N2. N2, the output of N2 is 1 NAND 1, and that would be a 0, and that is a change, and as a result, this needs to be bold-faced to indicate that, yep, the output got changed. The rest of the circuit, everything is just maintained like the previous row, so I'm just copying everything like that. And these are all going to be question marks again. That's because of the node propagational delay. And now we have to look into what is going to be updated because of node connectivity. In other words, we look at how the wires are connecting between the ports, and then we try to figure out what is going to be changed. Well, we only got one that is changed here, which is in purple color. So we look at all the other things that are also in purple color and say, okay, all of those are going to change. We only got two purple color ports, so both of these are going to be changed. And the rest, we just copy the same as before. So when you do this in an exam, you don't have to copy per se. You can just basically leave those blank if you can track your changes by looking up for the last update. I personally prefer to do it this way, even though it's a little bit tedious. It does make the analysis a little bit easier. But everybody has a different preference, so you guys can decide how you want to do things. So once again, after a propagational delay, we look at the input of all the devices. N does not have an update to its input, okay, so it's fine. N1 does not have any changes to its input. N2 does not have any changes to its input. On the other hand, the SR latch has one of its input changed, so the outputs, both of them, we need to try to figure out what is going to happen to the outputs for the SR latch. So are we still doing okay so far? Because I've been just yakking and yakking and yakking. I'm basically doing what Logisim does, except I'm just talking out loud. All right, so let's look at the SR latch here. Okay, the SR latch now has a 1 for the S pin and a 0 for the R pin. You can look up a truth table to find out what the output is supposed to be. So can someone tell me what the output is supposed to be in this case? What is going to be the value of Q? 0, very good. And then the other one is going to be a 1, okay? So it is useful, it's even though you're going to have open book and open notes again for exam 2, I think it is going to be, it will improve your score if you can be more effective at finding, what is going to happen, based on the input of a device. So you might want to have the truth tables included in your quote unquote cheat sheet, just so that it's easy to look up. All right, so these two are the only ones changed. The rest are going to be exactly the same as before. So in a spreadsheet, there are quicker ways to do this in a spreadsheet, but I'm not going to do it, just because you won't be able to do it on a piece of paper either. All right, so now we are ready for node connectivity again. In other words, we're just spreading that change around because of how things are wired up. So we can see this is a purple. Nope, this is a red. So we have to look for the other thing that is also red. There's only one more, which is here. And then this is in gray. So we have to look up the other thing that is also gray and get those updated. So all of these are bold-faced because they're all changes. And then the rest, well, we just maintain the state as before. So 1, 1, 1, 1, 0, 1, 0, 1, 0. Okay. So now it's time for another propagational delay, and we look at all the components, and we try to identify any component that has at least one input pin changed. So we look at all the devices, N has not changed its input for a while, okay? Not a problem then. N1 also doesn't have its input changed for a while, not a problem. N2 does not have an input change, also for a while. And then SR does not have an input change anymore. Okay, it had one happening in the previous propagational delay, but not this one. So we are now done analyzing all the devices. None of them has any change, for the input pins, and as a result, we are now also at a steady state. So are we okay so far? Does everybody understand why we are now also at a steady state, which means we have already concluded all the changes have already finished their propagation. So the pond is stationary or still again. Just imagine you throw a rock, into a pond that has, some other features. The ripple, hits, something, and then it bounces back, and they all bounce around. We are now done. Okay, all the bouncing around is all done. So the pond is mirror-like once again. Is that okay? All right. So there's a third state because there's a point to this entire exercise. So we are going to track down the third step of the whole thing. And this time we are changing, okay, this is not supposed to be boldface because it's the same as last time. So this time the only change is to the first pin, which is our data pin. And obviously we are now scrolling the thing off the screen, which means it is the time to turn this feature on. So I can scroll the screen on one side without affecting the other side, like so. It's a pretty nifty feature, kind of handy, kind of useful. All right, so the input change is, okay, so I'm just going to mirror the other ones for now because I want to really, really separate the steps and the phases so that way, you guys can also fully understand what's happening. So now we have node connectivity and, we update all the green ones, right? So this is green, and this is also green. So all of them are going to be bold-faced because they are all changed from what they used to be. And the rest, they're the same as what they used to be. So I'm just going to copy all of those without bold-faced. 0, 1, 0, 0, 1, 0, 1. And then the next stage is a PD or propagational delay, which means we wait a little bit of time. And once again, we are trying to identify components where at least one of the input pin has changed. Okay, so we look at all the components. Okay, my recommendation is not to use the diagram to kind of try to shortcut, okay, to find out what has changed. I would just kind of use this approach and look at every single component and check to make sure that it has or has not changed. So N has changed its input, so we need to go figure out the output. And 1 also has one of its input pin changed, so I need to go figure out its output. N2, nothing. The SR latch, nothing. So now we have to go back to the underscores and find out, okay, is N going to update its output? If so, what is the new output? So in this case, the new output is going to be a 0 because N is a NOT gate. In this case, N1 is also going to become 0 because it's a NAND gate. So 1 NAND 1 is the negation of 1 AND 1, which is 0. So both of these are changes from before. So we highlight those. The rest we do not highlight because they are not changed from before. So they are just copied from the previous row. And then we have to do the node connectivity thing where we go to each output pin that has changed, and then we identify everything else of the same color and update all of those. So this is orange, this is also orange, so both of those would become 0. This is yellow, and so is this one, also yellow. So both of these would also have to change. And now we highlight all of these because all of these reflect changes from the previous state. And then the rest we just copy, like so. And there we go. So after a certain delay, okay, because now that the node connectivity part is done, after a certain delay, we go back and look at every single device and we ask, is at least one of the input pins changed? And if so, we need to look at the output and go like, okay, what potential is changed, for the output? So we look at N. Well, the input of N has not changed, so we're good there. And then we look at N1, the input has not changed, so we're good there. We look at N2. One of these input has changed, this one. So we need to kind of figure out what the new output is supposed to be. And then we also look at the SR latch. One of its input also has changed, which means we better keep track of both of its outputs. And so we have 3 spots to do the computation. So this is the first spot, which is the output of N2. One of the input of N2 is a 0. So that means the output is going to change to a 1, and that is a change. And then here we have both of the input pins of the SR latch changed to being 0, 0. So that means the output is going to be 1 and 1. And this is a change. The other one is not. So I'm only going to highlight one of them. And then the rest of the circuit remains the same as before. So 0, 1, 1, 0, 1, 0, 0, 0, and then 0 and 1. And then we have to look at node connectivity again. And so we look at the purple one, which is changed from before. It's going to force a change over here. We look at the red one. It's changed here, so we are also looking at a change over there. So we need to highlight every single one of these, like so. And then the rest, we just copy, which is a little bit tedious. I mean, if you guys have any questions at any time, please go ahead and ask, because um, otherwise this is going to be like super duper boring. All right, so once again, after a propagational delay, we try to identify components where at least one input has changed. Nothing is happening to N, nothing is happening to N1, nothing is happening to N2, but something is happening to the SR latch, because one input of the SR latch has just changed from a 0 to a 1. So that means I need to look at the output of the SR latch and try to figure out what the output is going to be. And then nothing else is affected. So now we can just kind of go back and focus on, excuse me. It's going to be this output. Did I? Okay. I'm just looking at this, and I think that needs to be changed too. All right. I'm just not sure why it is both faced in both lines. That's okay. I think I got it. Okay, so we look at the SR latch, and right now the SR latch has the S pin being a 0 and the R pin being a 1. So the output is going to be a 1 and then followed by a 0. So this is the update. And that's it. That's the only thing. That's the only change. Everything else, remain the same. So we can copy once again, a bunch of the ones and the zeros. And now we perform another node connectivity change. So we try to see what else we can spread. So we can see this pin is changed, and all the gray ones need to change to 0 as well. So this is a 0. This is also going to be 0. Both of those should be bold faced because they were changed from before. The rest remain the same. And 1, 0, 1, 1. And here's a 1. And now we have to go through another propagational delay. Even though we are pretty sure everything should be steady state at this point, we still have to kind of go through the analysis just to make sure. So we look at N. There's no change to N because the input has not changed. We look at N1. Both inputs have not changed, so its output is going to stay put. N2, same scenario. The SR latch has not changed its input either, so we are good now. We do not have, we're done with the propagation change, the change propagation at this point. Are we doing okay so far with this analysis? Yep.
Any advice on how we can color code on like a test or something? Because I feel like um, that many pins, like it's really helpful to have the colors and know which one is mapped to which.
Mm-hmm.
How would we like do that on pencil and paper?
On paper, well, um, my first reaction, my first answer was colored pencils
Oh,
or crayons. Um, but I guess that may not be practical. Um, you can still use a diagram, so you can basically just hand draw a diagram to kind of help you understand, how things are connected. Um, and different people have different way to track it. Some people really like the picture because they are more visual. They look at the connectivity through the wires. And some other people like myself, I just work with the color coding just fine without a problem. Um, so it's kind of up to you. Kind of up to you. Yep.
follow up on
Oh, okay, you first, and then you go ahead.
can we like print out like this thing like but without all the numbers and then show our work on it?
Well, you won't be able to do it because you don't know what the circuit looks like.
So,
Yep.
yeah.
I think you can also color the whole column from the spreadsheet. If you press
Correct.
the letter.
But that's assuming I'm giving you the table.
Yeah.
So I suppose I can give you the table. That will work. And I just got new toner for my printer, so we can do that. The new toner cost about $600, but it's good for like 6,000 pages, so it's not a bad deal. Yeah, I can do that too. So when we get closer to exam two, we'll kind of get back to this one. If you guys want to revisit, what is the best way to track, the connectivity between the ports. Um, One thing about the exam is I will most likely, let's say for certain, that you will see a design that is not something from the module itself. But the process to analyze it will still be identical. So you're basically just doing the same kind of propagation analysis, change analysis, but on a circuit that is not something that you have seen before. Okay, because I'm testing you not to see if you can memorize all the zeros and ones. I'm trying to test whether you know how to do it or not. All right. So that means, in this entire process, it is about how it is done. Okay, that is the important part. It's not so much about the actual steady state and whatnot. All righty. Any questions about this little exercise? Yes, yeah.
So it's going to be like a combination of like different, like like the other class session where we had like a different circuit. It's not exactly the SR latch.
I will give you a circuit of about the same complexity,
Uh-huh.
but possibly one that you have not seen before.
Okay.
It will still be made out of things that you know. So it will still be NAND gates, AND gates, OR gates, NOT gates. It's just that the way it's configured may not match exactly something they have seen in the module. All right. So you still need to understand how things are connected for one thing, and you still need to understand the process of figuring out how the changes propagate. But other than that, that's all I can say. So I'm not going to throw in a gate that you haven't never seen before. I'm not going to throw in like tax gate and the truth table is completely unknown. That would be impossible to track, right? So it's going to be some gate that you have seen before. And so far we have seen how many different gates? We have seen NAND, AND, OR, NOT, and NAND. Hmm? Exclusive OR. Yep, that's it. I mean, there are only so many gates, that's countable on one hand that we have used. All right. So assuming it is all right, because I'm not getting any contribution either way, so I'm going to assume that everything is okay. And then what we'll do now is we are moving on to the notes. So we are looking at the flip-flops and other basic memory devices. So what we have done is to go through this particular device, and I would say it's going to be very helpful if you can read section 5 and section 6 kind of on your own, especially section 5. So section 5 is interesting because you can turn this into an assignment on all by itself. Because I have these questions quite often like, but Tag, you're not giving us enough homework assignments. You're not giving us enough ways to practice. This is one way for you to practice. Let me describe what you can do as a practice. So the first thing you do is you look at this text description and turn it into a circuit. Okay? So we talked about this already, how to turn this into a circuit. Yes, if you track this as a spreadsheet, it's going to be a little bit longer, wider compared to what we have done so far because we have quite a few more devices. I mean, we have two SR latches, two NAND gates. It's not significantly more difficult, it's just a little bit more. And then in the exercise, what you can do is you can look at these two, okay? That's your initial condition, and this is the transition. Okay, this is the next step, and then you can figure out all the changes. You can follow all the changes because of node connectivity and propagation, just like what we did today, except applied to this particular circuit. So I would do that because the answer is already here. It is just explained in a text manner, which is really tedious. But in the table, you should be able to confirm what I state, what the machine, what each step is going to end up with. It should be consistent with the way you track it in a spreadsheet or whatever table you want to use. Does that make sense? Okay. So here's an exercise that's kind of built into the module. If one exercise is not enough, you can also follow up with another one, like this one here. This can be another exercise where the first step has both the clock and the data pin. Excuse me. The first step has the clock pin being a 0 and the data pin being a 1, and then the second step just changes the clock pin to a 1. So if you compare 5.1 to 5 and 5.2, the only change is the data pin stays as 0 for 5.1, and then the data pin stays as 1 for 5.2. But then you can see how you know what the edge sensitivity comes from. In other words, what, why is this circuit only sensitive and capture whatever the D pin has and reflect it to the Q pin when the clock pin transitions from a 0 to a 1? Okay, so doing that exercise will give you kind of the insight of how this circuit works. Now, if someone is thinking, I'm not saying that anyone is thinking, but if someone is thinking, but I can do this easily using Logisim. Well, even assume that you can use Logisim in exam 2, which you cannot. All right, so I can already feel the disappointment here. Even if you can use Logisim, Logisim only gives you the steady state. It does not give you all the transitions in between to get to the steady state. So Logisim can confirm the last row, confirm whether your last row is right or not in each step, but it won't be able to give you the intermediate steps at all. All right? So the intermediate steps is something that you have to work out. Okay? And that's the important part.
Will we have a spreadsheet for the exam?
Hmm?
Or will we have a spreadsheet for the exam, or do we have to get like blocks?
I think I will give you the spreadsheet, just so that you can save the time. So if I give you the spreadsheet, I can also color code the columns. So that way, it's easier for you guys to see, oh, okay, this is the same as that column because you can't scroll like the spreadsheet that I use here, right? So it's easier for you to lose track of which column is which column. But once I use like the same color for the entire column, it's easy to look up and go like, oh, okay, this is the N1 device. This is the input pin 2 of the device, and so on and so forth. Yep. That should significantly save you time because the table is pre-formatted. All you have to do is to figure out the zeros, the ones, and the question marks.
You can probably write like node connectivity or and gate, like nature of the gates and stuff. Do we have to do the proof?
I have not decided yet how to describe the circuit, but more likely than not, it can look like that.
Oh no, sorry, I was talking about like node connectivity.
Oh, right, yeah, but that's up to you. Some people like to combine the node connectivity and the propagational delay, to make the table shorter. That would be doable as well. Yep. All right. Those are all very good questions. I have to make a note to myself to remember to kind of pre-format the table, color code everything so that you guys have a good starting point for that. All right. Any other questions? Okay. So if there are no questions, we are going back to the module. I really like the vertical tabs because it just makes it so much easier to see which tab is which tab. And of course, people can say, but Tag, you're the only person who has, this many tabs open in a browser. This is nothing. You haven't seen my actual browsers when I'm doing research and actually doing coding. 30 tabs is not unusual.
Is that like a plugin that you're using?
Yeah, it's an extension of Firefox. You can get the same kind of extension for Chrome, and there are several extensions of the same nature. So they all do slightly different things. Some can save the entire tab tree, and some, so you can reload it. So once you save the tab tree, next time you log in, then you can just go like, okay, I want to restore all the tabs the same way as before.
Yeah, no, it's like 20 tabs plus easy.
Yep, and I have multiple windows. Each one has 20 or 30 tabs. I actually have one thing. I did not install it here. There's a little extension that allows you to do a search of all the tabs of the same instance of Firefox or Chrome, and I found it to be super useful because I just completely lose track of where's my Outlook tab again. Search for Outlook, and it just identifies the tab and brings me there right away. Yeah, yep. It's those are very useful tools for sure. All right. So the thing about an edge-sensitive D flip-flop is it is edge-sensitive. So if you look at an edge-sensitive D flip-flop, it has 3 input pins. Okay, so let me try to give you um, the state diagram of a edge-sensitive D flip-flop. Okay, flip-flop. There we go. But before we do that, let me take roll first, just so that you guys have a little bit of breathing space. Um, and I changed the format of taking roll, and you guys know this already. This is not really, really new. So today is the 13th, and I just have to show you what access key you're supposed to use. So the access key is delay. I'll put it on the whiteboard just so that you guys can get back to it. Okay, so this is the access code. And I'll give you guys until the end of the lecture to do that. So that will be 10:20 a.m. There we go. Save and publish. So off you go. Go ahead and take roll. And I am going to switch back to the modules. Actually, I'm going to work on the truth table for an edge sensitive D flip flop. So SD has clock, has Q, and not NQ anymore. Okay, so we have a 0, 0, 1, 1. Assuming you guys have taken row already, this is one way to look at the truth table. I know we haven't really talked about what the RE is, rising edge. Okay, in an actual diagram, when you look at the data sheet of chips and whatnot, the rising edge is usually graphically represented as something like this. Okay, this is what they use to represent a rising edge. So the truth table is basically saying if the D pin is a 0 and the clock pin has a rising edge right at the moment of the rising edge, the output will become 0. That's what it means. Okay, so and then the 1 is the same thing. If the input is a 1 and the clock has a rising edge, which means it is transitioning from 0 to 1. Right at the moment of the transition to 1, the output pin would also update to a 1. For everything else, the Q pin is going to be no change. So you can play with your D pin all day long as the clock is not experiencing a rising edge, nothing happens to the Q pin. Is that okay? So compared to a level sensitive D flip-flop, the two mechanisms control two different things. So think about an orchestra. Okay, if you're in the orchestra, you are playing a certain instrument. Okay, in the orchestra. So when the conductor is staring at you, you know, then the enable is turned on. In other words, yes, I am talking to you. Okay, so the enable allows a mechanism to specify which D flip flop should pay attention. Okay, and then the clock controls the timing. Okay, the clock basically specifies when are you supposed to update. In other words, to any D flip-flop, you can now say, yes, I'm talking to you, and update now. So for all the other D flip-flops that you do not have the enable turned on, the clock can go up and down, they're not paying attention. Okay, but for the one that is paying attention, because the EN or the enable is a one, that it still won't do any update until the clock experiences a rising edge. Is that okay? So the two mechanisms control two different things. One is quote unquote spatial. In other words, which one of you should be paying attention is spatial. When you're supposed to update, that is temporal. So now we have both spatial and temporal control over which device should update and when it should update. Are we good so far? Kind of? Okay. So with that understanding, now we can go back and take a look at the next design, which is, okay, let me go back to here. So the next design, as you would probably expect, is the clocked and gated, which is level sensitive D flip-flop. And for this one, I did not even bother to use the text description. But this one, since it's already represented like this, you can also make a spreadsheet out of it. Okay, you can make a table out of this. And the whole idea is if a D flip-flop has enable being a 0, it's not even paying attention. It's like, okay, whatever you want to say, I'm not paying attention. The clock can go up and down, nothing happens, okay? If the enable is turned on, which means it's a 1, then whenever, okay, at the very moment the clock goes from 0 to 1, it will mirror the data to the output queue. Let me say that one more time, okay? If enable is a 1, okay, and its level is steady, you present a data value here, it can be a 0 or 1. So you're basically asking the device to remember a 0 or 1. That's what the data pin is for, to specify what you want it to remember. The clock is controlling the timing. When the clock goes from 0 to 1, at that very moment is when the data pin or whatever value is the data pin has is going to be reflected to the Q pin of the entire device. All right? All the other time, okay, nothing happens to the output of the Q pin. If the device is disabled, clock can go up and down, it doesn't care. If the clock pin is not going for a rising edge, it doesn't even pay attention to EN as long as the clock is not at a rising edge. Is that okay? But you do not have to take my words for it. Who likes to use that phrase? Don't take my words for it. In the Reading Rainbow, oh, you guys don't watch the Reading Rainbow? PBS, Public Broadcasting, PBS, what is the S? Station, maybe. Maybe. You guys don't know that? Okay. Reading Rainbow. Don't take my words for it. I got to show you this because this is something.
Before you renew Amazon Prime, watch this. Look, I love Amazon Prime. Free 2-day shipping is great.
Reading Rainbow is back as an app. But can it save children's literacy? We ask LeVar Burton. This is Media Beat.
Look, things change.
Anyone with a camera and a computer
We now
is a good
know we
idea.
should pay attention
What's
to
the
where
user
we all
value
do may evolve.
LeVar Burton, again, thank you for joining us.
Pleasure.
So let's
Oh,
Yeah, if you just go back,
okay. How do I go back?
just
Back the button?
Here's some other books that you might like, but you don't have to take my word for it.
There you go. That's what he says every single time when he introduces a book is don't take my words for it. So I don't want you to take my words for it too, which means in this case, what do you think you can do to basically look at this particular design and go like, I'm not 100% sure that what Tech told me is right. So what do? Well, there are two things you can do. One is easier, the other one is a little harder. The first one is to recreate the circuit in Logisim. That'll be the first thing to do. Okay? So once again, this is a recommended activity for you guys to do. Does it mean that you have to do it? Is it mandatory? The answer is no, because your grade is not mine. I'll just be brutally honest and say that. Okay? And if you think you're getting offended, I'm sorry. But it is important, okay? It's important that you actually make this circuit in Logisim and play with it and confirm what I said, okay? In order for the data pin to update the Q pin all the way up here, you need two conditions. First, EN has to be a 1. 2, clock has to experience a rising edge, okay? So that means all other time, okay? Doesn't matter what you do. All other times, if the EN pin is a 0 or the clock pin is not going from 0 to 1, the data pin here should not have any effect on the Q pin as the output of this device. That is my claim. How do you check that claim? Logisim is one way, but that's the easier way. The harder way is to do what we just did. Okay, use a gigantic table, track down the changes, track down what's going to happen for each propagation or after each propagational delay, and verify that you understand how the mechanism works. Okay, so this is highly recommended. We do have like 4 days before we meet again next Tuesday, like 5 days, 4 days. So I would use those 4 days and just kind of go through one example, okay? Are we good so far? All right.
And that's a really ingenious circuit too.
Yep.
Really
Yep, it is. So this circuit is close to the final stage, the fully evolved form, but it's missing one thing, because if you build this circuit, it will still give you an error when you first start up the simulator, because nothing is giving it an initial state. So we still have this problem. You turn on the computer. What is the content of RAM? What is the content of the registers? They're all random. You have no idea what they are. So we need one last mechanism, which is to reset a reset mechanism, and that is this particular thing. You can call this a resettable, edge-sensitive, and gated D flip-flop. There we go. So if we look at the input pins, okay, forget about everything in the middle for now. But when you look at the input pins, this is the reset pin. When the reset pin is a 1, it ignores everything else. And it just says, okay, this SRC flip-flop, you better reset to 0. The output pin Q is going to be 0 whenever the reset pin is a 1. Is that okay? So that means, quote unquote, normal operation should have the reset pin being I think I said it the other way around. When the reset pin is a 1, it resets the, the last SR latch so that the output becomes a 0. When the reset pin is a 0, then you're in normal operation mode where it is exactly the same as the design right before that. So in other words, this is almost exactly the same as the design in section 6, except it has one extra thing, which is this part of the circuit being tied to the reset pin. That's the only addition to this circuit, which allows it to be reset by an external signal to basically say, okay, I want you to initialize yourself to 0. Go do it now. That's what the reset pin is doing. Are we doing okay so far with this design? Okay. Now, I don't know whether you guys have the question of when you turn on a computer, who is responsible to say, yeah, everything, go ahead and reset because we need a known state to begin with. That mechanism is usually called a watchdog device. Okay, and you heard me right. It is called a watchdog device. It serves multiple purposes, but when you first power up a computer, that little circuit, which does not contain any processor and anything fancy, is just a delay mechanism. It holds the reset line. It holds the reset line to assert reset for a pretty long period of time by our standard, like half a second. But in the computer circuitry, half a second is a really, really long time. So that means there's enough time to convince every single device, every single thing inside the computer to say, yes, we all want to reset now. And it's a global signal to everything inside the computer. So everything in the computer is going to reset to the default state, may not be using exactly this mechanism, but something similar so that the entire computer has a known initial state to begin with. All right, so I'm not going to test you on the whole purpose or the design of a watchdog device. I do want to tell you about a watchdog device because that's a natural question, is who is going to trigger the reset pin? It is a kind of its own circuit inside the computer. On the same topic, okay, have you guys ever had the case where you almost bricked your phone or your game console and something, and it just won't respond, doesn't matter what you do, right? And then after a while, like usually about 20, 30 seconds or so, the device would reboot itself,
Yeah.
right? That's the watchdog doing its thing. So that is actually why the watchdog device is called the watchdog device. It resembles what we call a dead man switch. Do you know what is a dead man switch? Or something like that? So under normal operation on a phone and on most computer these days, the watchdog needs to be, okay, I excuse my terminology here, but that's actually technical. The watchdog needs to be hit every so often. So it's expecting to be hit, let's just say every 500 milliseconds, every half second or so. So your operating system, Android, which is Linux, or Windows, which has an anti-kernel, and so on and so forth, the operating system will respond to a timer, and it will go like, okay, it will try to play it safe, so it will hit the watchdog every 100 milliseconds or so. Click, 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 click. So if something really went wrong with your phone or your computer or your tablet, and it locks itself up so to the point where it cannot hit the watchdog every 100 milliseconds, the watchdog will time out. In other words, the watchdog is doing like, okay, let me see what was the last time I was hit. More than 500 milliseconds. What it's going to do next is to reset everything. Once again, it's going to assert this reset pin for everything on that tablet, cell phone, or computer, and therefore your computer has a chance to reboot from the beginning. Yep.
So in an infinite boot loop.
You can get into an infinite boot loop. However, the firmware of a cell phone typically has a way to escape from booting into the operating system, and instead it can boot into a bootstrap manager, which is a much more low-level type of program that is hard-coded on the phone. Now, that part depends on the manufacturer. So even between Android phones, depending on the manufacturer, some manufacturer has a hard-coded firmware that cannot be changed. It is immutable. Okay, it doesn't matter what you do, that portion cannot change. So you always have a chance to reboot or bootstrap to a loader, so you can reload, an existing or a more stable version of the operating system, and basically you can rescue the device. Some other manufacturers do not have a immutable firmware, so even the firmware itself can be updated. So on those devices, you can end up in a state where the device is bricked, BRICKED, which means you can't fix it unless you desolder the chip. Yep, yep. And you can also imagine how important that mechanism is, for computer systems, on a space shuttle. We don't have space shuttles anymore, but when we did have space shuttles, we do not want things to lock up. Now on phones, the funny thing is, on older phones, because I'm old enough to remember those, there's a battery compartment in the back. So if the phone really does not want to reboot, it just locks up. You just open up the back, take the battery out, just let it sit for a while, wait for all the capacitors to discharge, and now you can restart the phone from the beginning. When was the last time you change or take out the battery on a cell phone? 5 years?
When I had a Galaxy S5,
Okay.
then I changed to S8 and it already had a flashback.
Yep. And it's not like you cannot do it. It's very difficult to do it. Especially last time I did that was my wife's cell phone, and the battery was glued. I was looking for screws and things to disassemble. Nope, everything was snapped together and glued. Yeah, I did not like that. That was not a pleasant experience. Huh? Yeah, I have a heat gun. I was just really, really worrying that I would heat it up too much. Yeah, I have a temperature controlled heat gun for desoldering, so you can program the temperature to like down to the degree, but still it is kind of like it's still tacky, so you still need a little bit of peeling, and the peeling can crack the screen, and it's just not easy. I'll just put it that way.
I hate a lot of the modern design phones. It's like you need to have the right to repair your own stuff.
Yep.
And they just don't give that.
Well, they don't want you to fix the phone to begin with. Buy a new one. Why fix the other one? All right, so once we have that, okay, then we can have a gang or an array of those devices to store 1 byte. Okay, so this is the device called a register to store 1 byte. Now, you look at this and go like, wow, that's pretty hairy. Well, it's not really that bad, okay? Because when you look at the input pins, it's identical to the design that is in section 7. It's exactly the same. It's just that the data pin is not a single bit anymore. It is 8-bit wide. And I'm using a splitter, so the bit 0 goes to one D flip-flop, bit 1 goes to another D flip-flop, and so on. So I'm simply using the D flip-flop from the previous section to store 1 bit at a time. And this is just an array of those D flip-flops. So they all share the same reset pin, they all share the same enable pin, they all share the same clock pin. So all 8-bit will get updated at exactly the same time. Is that okay? All right? And then the output is constant, okay? It will just constantly, report back the current state of each of these things. So, whatever you're storing, Q is always outputting the content that has to be stored in the register. Are we doing okay so far with what a register is? Okay. All right. So at this point, we can now start to look into the processor itself. Let me go to a command line interface so I can actually show you the processor. All right, so this is the processor that you'll be working with all the way to the end of the semester. So I think, at some point you probably want to get familiarized with this. All right, so we have several things that we already know, and several things that we may not know yet, okay? So it has got registers. This is a register. Okay, let me use the pointer tool. This is a register. And when you look at a register, it has properties. This one has 5 bits, so instead of storing 8 bits, it only stores 5 bits. The trigger is rising edge, okay? So that means that when the clock pin goes from 0 to 1, that's when it updates its content. Label, that's just a name. Label font, I mean, those are not important, okay? So that means, we already have what we saw in the slide earlier. Let me go back to the slide first so I can show you exactly what I mean. This whole thing, okay, this ugly thing is essentially this thing here in the design. And we have a few, okay? There's a register bank here. So when you go to the register bank, you can see here's one register, here's another register, and another register. But there are things that we haven't talked about yet, okay? So what I'm going to do now is to talk about those items. And we'll start with things that are easier to understand, and then we'll move to things that are a little bit more complex. So there are two things that will serve as like a switch in a railroad system. One is called a multiplexer, and the other one is called a demultiplexer. So an example of a demultiplexer is here. All right, so as you probably imagine, the term multiplexer and demultiplexer means that these two things are related. And indeed they are, okay? So let's take a look at a multiplexer first. So once again, if you want to figure out, how something works in LogicSim, and I am going to check. Yep, I'm still recording. Very good. Just to be sure. So you go to library reference, and it opens in the other window. So I just need to put it back here. And then you go to plexers, okay? So when you go to plexer, it will explain what a multiplexer is, what a demultiplexer is, and a decoder is kind of like a demultiplexer. It's a specialized demultiplexer. Okay, we'll start with the multiplexer, okay, just because it's the first one on the list. So a multiplexer is basically a switch. You have multiple input pins, one single output pin, and then you have a select signal. So it allows you to specify which input connects to the output. That's its job. Is that okay? So just like at a railroad intersection or junction, there might be several rails connecting to the switch. So you get to specify which train gets to go through the junction to continue its journey down the other rail. Is that okay? Multiple input, one output, and then you also have a select signal, which is the one under the gray pin. That is a select. In other words, it will tell the switch which input connects to the output. Is that okay? All right. So a demultiplexer is the opposite. You can even look at the symbol. It's like, oh, that looks just like a multiplexer, except it's opposite. Well, that's exactly what it means. It has one single input and multiple outputs. So it allows you to say, okay, we got one input here, but which output does this input connect to? And you have a selection mechanism, so it can select which output connects to the input. In other words, multiplexers and demultiplexers are directional. Whereas in the rail system, it is not directional, right? Because a train can go one way or the other. But in terms of an electrical circuit, things are directional. But the concept is the same, okay? You're simply selecting which input connects to one of the multiple outputs, or the other way around, where you control which output, um, the other way around is which, what did I say earlier? Okay, scratch that. Let me start from scratch. So it allows you to specify which input connects to the one output, or it allows you to specify which output connects to the one input. There we go. Is that okay? All right, so let me ask you this question. If you have 8 inputs and one single output as a multiplexer, how many bits do you need to specify which input connects to the output? Let me say that one more time. You have 8 inputs, okay? So 1, 2, 3, 4, 5, 6, 7, 8. You got one output. Okay, this is not working. Let me do it one more time. There we go. Okay, so everything goes in this direction. So you are basically the person here saying, okay, tell me which input connects to the output. The question is, how many bits do you need to specify 1 out of 8? Well, think about this, okay? We can label these things with numbers, right? This is input 0, input 1, 2, 3, 4, 5, 6. I'm missing 1. This is 7. There we go. So let me just double count. Yep. So now we have 7 inputs. The question is, how many bits do I need to specify which input connects to the output? So here's the gray dot. So the gray dot, it needs how many bits? Another way, yep. Close. 3. Yes. We need 3 bits because 2 to the power of 3 is 8. So that means with 3 bits, we can now designate one of the inputs to connect to the output. So if you prefer, we can look at this as 0, 0, 0. This is 0, 0, 1, 0, 1, 0, blah, 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 all the way down to 1, 1, 1. So that is why we need 3 bits here to specify which one of the input pin connects to the output pin. What about the other input pins? They're just not connected to anywhere. Is that okay? All right. So some of these devices also has an enable. So the gray pin here is the selection. So the width, the bit width of this port depends on how many inputs we have. And the number of inputs are always a power of 2. So you start with 2 inputs, then 4 inputs, then 8 inputs, then 16 inputs, and so on. And then the gray dot is basically the log 2 of the number of inputs. Is that okay? So what about this pin here? This pin here, this is the output pin, that's the easy one. But what about this pin here? That is what we call the enable pin, which means if the enable pin is turned off, the output can not connect to any one of the inputs. So there's that special mode of none of the input connects to the output. The output is simply doing absolutely nothing. So you can basically have that's optional. So not every multiplexer has that enable pin because without the enable pin, that is always enabled. With the enable pin, it simply means that you have a choice of whether the output is active or not. Is that okay? So now we got the multiplexer and the demultiplexer. The demultiplexer is exactly the same except in the opposite direction. Okay, that's all. So it still has a little gray dot here, which means this pin here or this port is the log 2 of the number of outputs. And then this pin here, once again, is the enable pin, which means if there's a pin like this for enable and it is a 0, that means none of the output connects to the input pin. And of course, the description also describes that. So the multiplexer and demultiplexer are pretty easy to understand. once you understand what they are supposed to do, a decoder resembles one of those two. Which one does it resemble? Does it resemble a multiplexer or a demultiplexer? It resembles a demultiplexer, and you can see that the only difference between a decoder and a demultiplexer is there's no input. So what do you think is the implied input in this case? It's a 1. It just has an implied input of a constant of 1. And we call it a decoder just because, it serves a role that usually is called decoding. All right. So, and then another device which will take a little bit longer to explain. One is RAM, and the other one is ROM. And I think we can go ahead and describe a ROM first because a ROM is the easiest one to describe. So a ROM looks like this. It has got 3 ports. One port is called A, which stands for address. One port is called D, which stands for data. And then one port is called cell, which stands for select. So when select is a 0, that means the device is turned off. It doesn't pay attention to the A port, and it doesn't do anything with the D port. So when select is a 0, it is as if the device is not even there. So that's an easy one to explain. The A port specifies which location you want to access. So a ROM is like an array. It's like an initialized array. And then the A port is what you put inside the square brackets in C or C++. It specifies, okay, we got a bunch of elements here. Which one do we want to access? The D port is the value of the element that you have addressed. That basically describes what a ROM do, okay? What is the full name of a ROM? I just want to see if they have explained here. Nope. Okay, very good. So what is the full name of ROM? It's an abbreviation of something, but what is it?
Read-only memory.
Exactly. It is read-only memory, which means the content is not supposed to be changed. Okay? So now we move on to RAM. We are close to running out of time for today's lecture, but I can at least get into RAM. So RAM is a little bit different. It has got more ports. Let me see which one I want to look at because there are 2 of these, and they differ by the in signal here. So we want to use the left-hand one because that's the one that is used in the processor design. So this time we still have the same cell, which is basically if cell is 0, the device doesn't pay attention at all. It is as if it is not there. We still have the A port to specify which location in RAM do we want to access. We still have a D port that deals with data, but this time the D port is bidirectional. In other words, it does not just report out what is the content at the location. You can also use the D port to specify the new content at a certain location. And that's why it's called bidirectional. But this time we also got 2 extra pins or 3 extra ports here. This little thing here that looks like a triangle, that's the clock. Okay, that's just how clock is usually represented in a circuit. It's like a little TP or little triangle. That's the clock, which means it controls the timing of when you want the RAM component to update its content. Once again, in the design here, it is on the rising edge. Okay, so we use a rising edge for that. LD is out. Okay, so what you see here is out is actually LD here. It controls the direction of the operation. In other words, you can specify a 0 when you want to change the content of RAM, but you can also specify a 1 when you just want to read the content of RAM. So it's a direction control. LD or out is a direction control. And then clear is also present here. That's the reset pin. Okay, if you ever want to change the content of RAM, everything back to 0, you put a 1 to the clear pin. It's the same thing as what we call reset earlier in the class, but it resets the entire content of RAM. You lose everything in RAM. All right, so on next Tuesday, I'm going to experiment a little bit in class with RAM and then we will have an actual lab next Tuesday so that you can get familiarized with some of the components. Because eventually what we are going to do is we're going to use this diagram or use this particular design, and you're supposed to be able to track changes throughout the processor. Okay, but first of all, we have to kind of understand what components are inside, and we have already identified the components. This is an adder, this is a register, this is an AND gate, another register, this is an adder, multiplexer, a whole bunch of multiplexers and some demultiplexers, and then we have the RAM and then the ROM. So each one by itself is not too difficult to understand, but the operation as a whole takes a little bit of time, okay? It does take a little bit of time to understand what it does and how it gets the job done. So that's going to be something that we'll do the next 2 weeks or so. We're going to get familiarized with the processor, and then after that, we'll start to understand the assembly language that is designed for this particular processor. And then after that, we'll start to convert C code into the assembly code so that we can actually run programs in this processor. It only has 256 RAM locations, 256 bytes of RAM location. When was the last time you hear we count the amount of RAM in bytes, as opposed to, in your generation, gigabytes, which is a billion of bytes. This thing has 256 bytes, and yet that's enough to run the Tower of Hanoi algorithm. Yeah, the Tower of Hanoi, you got 3 poles, right? And you get a bunch of disks. So the idea is to move a stack of disks from one side to another side. But there are rules that you have to play by. You can only move one disk at a time, and you can only put a smaller disk on the larger disk. So you can't just take the entire stack up, drop it over to the other pole. Nope. You have to kind of play by those rules. And as it turns out, this processor has enough resources to do that. So we're gonna.
I tried solving the Tower of Hanoi problem once. That was interesting. I didn't want to look at any guides or anything. So.
The Tower of Hanoi problem is one of the classic recursive algorithms, which means it takes a special way of looking at the problem. And the way you look at, okay, I can explain that just briefly because you asked. So the idea is let's just say you have a stack of disks, right, from one. So you move everything except for the largest one to the middle pole, and then you move the bottom one all the way to where it's supposed to go, and then you move everything from the middle pole to the last pole. But then you guys would say, but I thought we were not supposed to move multiple disks at the same time. Yes, that is true. So what you do is you turn the bigger problem into a smaller problem. Because once you have the largest disk moved to the middle pole, then the problem of moving the remaining portion, the other way around. So you need to do the recursion first to move everything but the largest disk to the middle pole using the last pole. Once you solve the problem, which is a sub-problem using the same function, then you move the largest disk all the way to the destination, and that's just one move. That has no recursion in it. And then the sub-problem becomes you take the entire stack of things in the middle pole, using the first pole to move everything to the last pole. So basically, it is breaking up the problem into 2 recursion and 1 simple step. And that's the recursive approach. So in this class, if you say, I really do not know how to write recursive algorithms, relax, you won't be asked to. But you do have to be able to translate given recursive functions in C into assembly code. And we'll get there step by step, okay? So if you're new to C or you cannot remember C because it was a while back, now would be a good time to kind of get reacquainted with the C programming language. All right, so I'm done with today's lecture. You do have the positive exponent lab due next Tuesday. So if you're stuck, working on that particular program and you want me to take a look at your program, today's lab would be a perfect time for that. Because I don't want to stay up next Monday, because people are saying, my program is not working, can you help me? No, I'm gonna go sleep now. Good night. All right, so I'm gonna stop the recorder. And if you want me to take a look at your program that is due next